Okay, so this is going to be our 26th lecture on power system operation and control. Today, we are going to start the new topic, that is hydrothermal scheduling, and we have completed previously the security constraint optimal power flow, where we have already seen preventive control, corrective control. We have seen this flow chart, and today in the tutorial will be solving one numerical on this. So this will give you a better picture that how exactly the preventive and corrective OPF works. So this will give you an understanding. So is there any doubt and queries on this preventive and corrective rescheduling? You got the complete picture, right? How security is ensured in power system. So I'm just, if there is any query, you can ask. So we saw two approaches for preventive OPF, and one approach where only the critical contingencies will be taken care, and in the second approach, we actually restore the feasibility. Restore the feasibility means we only initially we a system operator ensures that 80% of the capacity will be used for, and the 20% will be kept as a margin, and this 20% can be used in case of emergency or in case of some critical situations. So those situation can be used and exploited. So generally, let's say for the, if you talk about the lines, so generally, just to give you a quick understanding, again, so we, if a line is having 100 megawatt capacity, so we generally operate at 80%. So let's say we'll be operating at 80 megawatt, right? But in practical situation, you can actually go till 90 or 95 even. So and that extra 20 megawatt is kept as a margin, because obviously in real time things are fluctuating, renewables are fluctuating, loads are fluctuating, every component in power system are actually fluctuating. So in that fluctuating situation, you cannot ensure that line will exactly be able to, we will be able to cap the power flow at 80 megawatts. So there will be a situation where it will go beyond 80. So these margins you can exploit. Also, one important point here is that this thermal limit, generally this thermal limit what is given by the manufacturer, it is also a bit, basically he as a manufacturer, he also ensures some margin. So actually the thermal limit will be somewhere around 120 or even more. So after you cross 120 megawatt, then the wires will start melting. So they actually keep some margin here also, which can be used for small time duration. Let's say for 1 minute you can go beyond 100 also, and not for longer, because heat is basically I square RT. So I square R is the power, and T, when you multiply it by time, the time duration you apply that current, it, the heat depends on that. So for smaller duration, you can allow the line to go beyond that, and then you can bring the line back to the limit. So that can be at times exploited, but this is generally a risky zone. So this zone is a risky zone. So system operator generally do not go in this zone, but he plays within this zone. So this zone is where he actually plays its game, and try to ensure the security of the power system. Right? Any queries on this? Okay, if not, then let us start the new topic, which is hydrothermal scheduling. So, any guesses or any idea what exactly we are going to do here? Why we want to add a term hydro here? What differences does it make? Anyone? Any random guess? No problem.
Sir, I think for the critical scenarios that that you are, for example, you are in preventive rescheduling,
Mhm.
so we need backup. So I think thermal scheduling it will be so fast to retain the system or back up the system for that situation. When
Uh, yeah, means okay. You are actually answering it from the practical point of view. Yes, you are right, but specifically we are studying hydro separate to means whatever scheduling what we have studied till now in security considered OPF or economic dispatch, whatever we have studied, all these OPF, we are mostly focusing on thermal generators. Thermal means either it could be coal based, either it could be diesel based, either it could be gas based or nuclear based. So all these power plants kind of you can call them as a thermal generator, because here in some way or the other you burn something and then you generate heat and then you run the machine or run the generator. So that's why you can call them as a thermal generator. So hydro, why we are adding? Because hydro generation is a separate entity itself. Why? Because its operation does not depend on natural features of like thermal generator. Because for example, thermal generator, if let's say you want to ramp up the thermal generator, you know that if you burn the coal at this rate, and then this much amount of steam will be generated, and this much amount of steam will lead to the increase in speed of the generator, and which will eventually increase the generation limit of the generation margin of the generator. So for example, let's say in thermal you are generating 10 megawatt and system operators tells you to generate to 20 megawatt. He knows exactly what he has to do to generate from 10 to 20. So that is exactly known to the thermal generators. Thermal generators, everything is in the control of the system operator, or everything is in the control of the power plant operator. But in hydro, things are not very straightforward. Obviously it depends on various factors, and those factors makes this hydro power plants different than the thermal generators. Obviously the answer what Adam gave is basically in case of emergency hydro is called, because obviously the reason is that hydro has a very fast ramp up and ramp down capabilities, and obviously it is cheap, and it is relatively cheaper than the gas and diesel based. That's why everybody encourages using hydro in case of emergency. And also these days we have lot of variety of power plants, but in olden days the ratio of hydro and thermal was very high, because most of the power plants used to be thermal, which is around 70 to 80%, and 20 to 30% were hydro, because there was no renewable and nothing, no batteries, no EVs, nothing was there, even demand response was not there. So only in the olden days only hydro and thermal were there. That's why this study even made make more sense for studying this hydro. And even today also the hydro percentage has increased, and lot of small turbine hydro power plants are there. For example, if you know this or not, there is a state called Punjab in India. I don't know if there is any student is there from Punjab here. If this state has, basically the name of the state is actually five rivers are there. So in this state they have actually new technology has came in the hydropower plant, where you do not need to build a dam, and without building a dam you can still generate power just by the regular river stream. You can use the speed of the regular river stream, and then you can generate power. So these small technologies are actually increasing a lot in hydro, and these capabilities of hydro power plants are tremendous, and we can tap those energies which are basically we are wasting. So all the rivers are there, we are wasting those energies. We can definitely tap those energies to generate even more power. and it is obviously clean. It is free of cost. Everything is comfortable in this, convenient in this sense. Okay, let us see what exactly differentiates hydro in detail and understand it more. Yeah, so this I already discussed that many systems have a mix of hydro and thermal generation. Especially in India, it is very significant that the ratio of hydro and thermal is significant. So most of the power plants are thermal in India and hydro. That is the biggest capacity. Nuclear is also there, but it is again more or less it is controlled. So I'll not go into that. But hydro is the thing which is creating some differences there. So again, the important point is that hydro resources are limited. Why I'm saying limited is because the dam, if you see, let's talk about the dam-based power plants. So dam capacity is limited, right? How much maximum volume a dam can contain, that is limited. So let's say if I generally the dams are built on a, let's say if this is the dam, so the water capacity what it can store here, this is limited, right? Because obviously if you store more water, then it might overflow. Or just a second. Okay, so it might overflow if you store more, or also if you store more, it might damage the dam. So that's why it is limited by how much volume you can store. And obviously the continuous water flow is coming from upstream. So this upstream water, you also need to uh, allow some small amount of water to go out as well, because of regulations and limitations of the hydropower plants. Like basically because downside of the river there are cities, there are farming lands are there, and everyone needs water for their day-to-day activity. So basically you cannot stop the river flow completely. So let's say in summer time where water flow is very less, you even then you cannot stop the water flow if your if your dam this area of water collection is less. Even then you cannot stop the complete flow of water. So that's the that are the some hurdles are there, and these hurdles make them a limited source. So that's why whenever we say it's a limited source, that means that you have to be very careful for using the hydro energy or hydropower generation very very carefully. Okay. And if we talk in terms of the cost is very insignificant. Obviously, there is no raw material. Obviously, the raw material is water here, and which is free of cost. So generally, there is no cost in the hydropower plant. There is only cost in terms of capital cost. Obviously, the building this dam takes a lot of time. So generally, it takes around 10 years to build a dam, and that building cost is there. And also on day-to-day activity some maintenance cost will be there, and also because you will be employing some manpower for your maintenance of that power plant. So those costs are there, which are there for any power plant per se. But here this power plant will does not have any raw material cost, which is the biggest portion in every power plant. But it has its own cost, which is from the capital cost point of view, because you have to initially invest a lot of money to build this dam, and this will start generating power only after 5 to 10 years when once it's completed. So obviously it takes a lot of time for that. But eventually it is very insignificant cost. So that's why it is very economical to build and to utilize this dam hydropower plants. There is also variety of hydropower plants, and all the variety of hydro plants are basically different. You cannot say that two power plants are identical because of the water storing capabilities. Those will be different for every hydropower plants. Even the because of that water storing capability, your generator size will be different. And also because of the location, the type of dam which requires to be built, that also differs, because obviously there are a lot of kind of factors which you have to take care for building the dam. So that's why there is no two hydropower plants are alike. And there could be also hydropower plants with storage also. So for example, let's say if you have like this type of dam. So let's say this dam is there. So there could be a storage type of dam where, let's say if there is a water pond here, or you can create a pond here. So here the water is there. So what you can do here is, if you if let's say in the night time where power cost is very less, so you can discharge the water from here, and then you have a big pump here by which you can pump the water again back to this pond. And during the daytime where the cost of electricity is high, you can discharge the water from here, and then you can generate power. So this is the type of storage of plants are also there. You can have dedicated storage plants also, where not only just this type, even if you can discharge and you can put the water here also. So these type of plants are also there. So they are just the storage plants. So basically it is like a battery where you will discharge whenever the prices are higher to reduce the prices, and you will charge or basically store water as a pumping action whenever the prices are very less. So this is these type of plants are also there in hydrothermal, and these plants are also of different type and categories are there in this. Yeah, this. Okay. So basically, there are three types of plants in hydrothermal scheduling. Sorry, in hydro power plant generation. One is normal upstream storage. So this is very simple, that you have a river stream and then you are storing water here, and this will discharge whenever you generate power. And yeah, so this is the normal upstream storage generator. Right. Another is cascaded hydro plants. If you see in Uttarakhand, most of the power plants are cascaded power plants. So basically, here we have a lot of rivers in Uttarakhand. So what they do is they have cascaded. Basically, one hydropower plant is there on top of others, and everyone will have every generator will be of different quality, different type, different generation capacities, different water catchment areas. Everything will be different in these power plants, but it will be in a series type of thing. We call them as a cascaded hydro plants. Here, whenever these type of hydro plants are there, you also need to take care of the water transport time delays. So let's say if this generator generates more power, so obviously if more power generation, that means more water has to be discharged, but that power that water will not reach here immediately. Obviously there will be some kilometers distance is there, and then water will reach let's say after some 10-15 minutes or 20 minutes, depending on the distance and everything. So then only this dam can generate a big amount of power. So obviously when water is enough, then only he will be able to generate. So these type of power plants require a system operator to ensure that this power transport time delay is also taken care of. So this is a very specific case and typical case what is actually you can see here in Uttarakhand. So here we have lot of power plants in a cascaded sense, hydro power plants in cascaded sense. And lastly, pumped storage plants. This I already explained. Even in the same cascaded river, you can have a pumped storage where you are pumping the water back to the water storage area. So here, basically, the same generator, because you know that the generator can be used as a motor also, if you take power from the grid. So the same generator can be requested to generate in a pumping action, and it can pump the water back to the storage area. So this type of plants can also be there, where pumped storage plants basically they recycle the water, and they generally generate at the peak periods, and they pump at the light load conditions. Obviously, generally at night they do the pumping action. At the daytime they do a generation action. Any doubts so far? Okay, let us see the. So anyway, this we have already discussed, that most of the pumped storage plant, they have two different cycles: generation cycle and pumping cycle, and they generally generate at peak load conditions and pump at the light load conditions. And so you can now understand that there are a lot of critical features in the power plants. So these three different type of power plants, we just now saw that there could be simple upstream storage, water storage plant could be there. There could be cascaded hydropower plants can be there. There can be pumped storage hydropower plants can be there. So basically these three are the different type of power plants, and even in that there could be different type of power plants in itself, because the capacity is different, the storage area is different. So a lot of factors can be there. Even also there could be the river also keeps on changing its direction. At times the river can change its direction, and you need to redirect the river to bring the water back to the dam area. Also there could be an issue of a spillage water. Spillage water is that if the dam means some water spills from the neighboring sides, and thus enough water catchment areas are not there, so that could be another issue which can take place. And yeah, so you can imagine there could be various factors which plays an important role in making a decision for hydro power plants. So therefore generally people use dynamic optimization problem, and or we can use a simple static one also, but generally people use dynamic optimization problems. So we are not going to go into that detail of this optimization problem, but I'll show you the basic model, how the basic optimization model changes because of hydrothermal scheduling. So let us see that, and try to understand what differences does it make. So before starting the mathematical model of this hydrothermal scheduling problem, one thing you have to understand here, that the power generation, PHI, is basically power generated by the ith hydropower plant. Let's assume there are various hydropower plants. So that power generation depends on a function of Qi and Xi. So here Qi is basically water discharge, and Xi is head of water. So water discharge is clear. So let me just draw the diagram here. So let's say if this is the dam and you have water here. So water discharge is basically at what rate you discharge. Obviously the rate will decide the power generation. But again, the head plays an important role. So this is the head actually. So head is the basically in the storage area, what is the maximum height of dam, or not height of the dam, height of water level from the point where this pipe is there, from which we have to discharge the water. So this head plays a big role. You can easily visualize this, that if head is higher, then the water rate of water discharge will be higher, because it will heavy volume of water will be there, so there will be enough pressure to generate power at a lower discharge also, because the rate by which the water will be discharging will be much higher. And if the head is less, then to generate the same volume of same power generation of power, or same value of power, you have to discharge more water. So you can imagine here that the input output characteristics of this hydropower plant is a function of qi and xi, which is not linear. This is non-linear. And also people also add to add complexity, the rate at which the power is the water is coming in the river, that rate also is considered at times for including the power generation, because obviously then the head will be maintained if the enough water inputs are there. So obviously this plays a very big role in deciding the power generation by a hydropower plant. So again, I told you here that this is a complex characteristics compared to the thermal power plant. Also, you need to ensure the cyclicity, because river flows changes during the seasonal basis. So let's say if it's a summer season, obviously water flow will be different than rainy season, and then winter season again it will be very less water flow will be there, because in winter season generally the water does not because here in India most of the rivers are basically is because of the melting of the glaciers. So obviously in winter season glacier does not melt and the water flow reduces in the winter time. But obviously not all the rivers. There are few rivers which comes out of the mountains, which does not come from the glacial melting. So those have different cyclicity features, and these rivers have different cyclicity features. So basically, the idea here is if you are planning for hydro generation, then generally a power plant owner or a system operator takes care of the long range problem first. So when I say long range problem, basically they plan the hydro generation for complete year, not just one day. They plan the power generation for complete year, because they cannot, if they forecast the season and they forecast the weather condition which is going to be there for complete year, and they plan their power generation, because they cannot exploit the complete power generation at only one day. So they, if they want, they can empty their water storage in just one day by completely utilizing the power, but they cannot do that, because it has to be ensured that they are running it all year long. So that's why they plan this accordingly, and they initially plan for long range problems, and then they go for short range problems, which is actually running for daily or weekly basis based on the load variation and seasonal variations. So this is the way they generally plan for hydro generation. And also from the regulators point of view, generally they have they in these hydropower plant owners are forced to keep the water available with them, because in case of emergency, as Adam was telling, that in case of emergency obviously every time hydro is called to safeguard the system. So that's why from the regulators point of view, they are always told to do not exploit or do not exhaust their water storage at any time interval. They should always ensure something. And also they are having some regulatory bounds from the basically government, because they have to, because obviously downstream of the dam there will be cities, there will be farming lands, there will be agricultural lands. So basically they have to ensure that everyone is getting the water. So those are additional regulatory obligations what these generators have to follow. So they have to properly plan their power generation, right? So that's what is the hurdle for the hydropower plant owners. Yeah, you can imagine that long range problem, because you are planning or forecasting the season of the complete year. So obviously the uncertainty will be higher, and in short range problem uncertainties are less. So what they do, actually they plan it for the complete year, and they fine tune their model by running the short range problems. So basically that way they run, and they keep they ensure that the water storage are sufficient for the power generation. So generally for these problems, hydro problems, basically you can imagine that the uncertainty will be very high. Uncertainty in the sense that you cannot predict the rain exactly, you cannot predict the solar, or basically the heat, the summer, how it could be, how it can be, how cold the winter can be, and how rainy a rainy season can be. So these things cannot be exactly predicted. So it is actually a probabilistic thing. You can predict with some percentage of confidence, and that prediction basically is a probabilistic one. So basically therefore long range problems are uncertain, and they are solved by probabilistic optimization methods, and the short range problems are more deterministic, because for predicting for 1 week is much easier than predicting for a complete year. So that is more of a deterministic one. Right, so we will not be going into the probabilistic one. I'll be showing you the example of deterministic one in today's class. Any queries as of now?
Sir,
Yes,
I have a
please.
question.
Yes, please.
We know that when the mud in dam, it also the problem.
Sorry, what is in the dam?
The mud when
Okay, mud. Yeah, yes, the sand.
yeah,
Huh.
exactly.
Yes, yes.
Because it will make a problem. How will it affect in our problem?
Exactly. So let's say if some landslide happens on the upstream of the river, so basically whenever landslide happens, it the water becomes very muddy, and it means water itself brings lots of mud, and because dam will hold the water, it will not allow the water to move. So basically all the sand gets accumulated at the bottom of the dam, and this is actually a big issue of hydropower plants. Generally what they do is basically they have these pipe or the water discharge at the bottom. So basically because as soon as they open the gates, naturally the water will flow, and they will take away the sand. So generally this happens, but even then what happens, because the accumulation of sand actually reduces the water storage capability of the dam. So at times, generally, or in every 6 month or every 3 month, the dam actually cleans the or removes the sand or the mud from the bottom of the dam. So they do that, and because it will create a problem, because it limits the water storage capability of the dam. So that is an issue, but they have this, they ensure this on every 3 monthly or 6 monthly basis. They clean the dam, and they ensure that the water storage capability are sufficient for their operation. Right, is this what you wanted to ask, or?
Yeah, exactly.
Yeah, exactly. So that comes under the maintenance part, and they clean it on some time, because generally this issue generally happens in the rainy season or in the winter season, because after the rainy season winter comes in, because rainy season generally all the landslides and muddy part comes from the upstream, and in the winter season when the rains are over, then they start cleaning it, and during the summer also they clean it, but generally rainy season they do not touch it, because obviously muds are continuously coming in the rainy season. Right, okay, good. Let's go ahead and see the so we, as I told you before, that we will be discussing on the short range problem and not the long range problem. Obviously you can imagine that this will be a huge problem to solve. we will be seeing the classical approach, and obviously the problem uh, will be will not be practical. Why I'm saying here not practical? Because we will be doing some assumption or approximation, because this input output characteristic what I told you, that this uh, power generation by hydropower plant depends on this Q and X. Q is discharge, X is the head of the dam. So that does not remain fixed. And obviously, whenever we are studying this, we are not ensuring that head part or the discharge part in our study. So we are ensuring that it is constant. So that is one approximation what we do. So that's why it is not exactly practical, but obviously some rough idea are generally there with the power plant owners, and based on that they plan their study. So yeah, so we'll assume that head is constant, so only discharge we will take as a factor for power generation, right? And also the water availability information in the dam, this information comes from the long range hydrothermal scheduling problem. So the yearly problem what you solve, based on that you get the information of water availability in the dam. So let us see this mathematical model, and let me explain you all the parameters and equations. Most of them will be clear to you. There is few things which we have to I have to tell you again. So for example, whenever we run this hydrothermal scheduling problem, the cost function is only to minimize the thermal power generation, because we are assuming that the hydro is free of cost. Again, so hydro has some cost, that is obviously their capital cost, maintenance cost, manpower cost, they will be there, but they are very less compared to the price what hydro power plants sorry, thermal power plants are asking for. So therefore they generally do not consider the price for hydro. I can tell you the practical values, generally hydro power plants generate at probably 10 paisa, sorry, 0.1 rupees uh, per megawatt, so, or per kilowatt, you can say this will be per kilowatt. So this is very less, zero point 0.1, even lesser than that, 0.1, 0.05 rupees per kilowatt. This is very less. And compared to the, if I talk about thermal generally generates at rupees. Again, it depends on the type of power plant, but it can start from 1 rupee to 3 to probably it can go till 4 rupees per kilowatt. Again, it is depending on the different type of thermal power plant. So obviously you can imagine the size, the quantum or the difference in the cost is huge. So generally we ignore the cost for the hydropower plants, but obviously if you want in a practical purposes, we can definitely include the cost of hydropower plant, and then we can add here the cost function of pH. So this you can add, and that can be added in the objective function. But for simplicity, I have ignored that part, and we are just including the cost function of the thermal generator here. So here let me just tell you the indexes I and J. So I is corresponding to Ni. Ni is basically number of sub intervals, basically the time intervals, and the Nt is the number of thermal generators. So basically J corresponds to the number of thermal generators, I corresponding to the time interval. So basically here you will see that PTIJ means the thermal power generation generated by the jth generator at the ith time interval. Right? Nomenclature is clear to everyone? Now with this nomenclature, obviously let's see the first equation here. This equation is nothing but just the power balance equation. Whatever thermal generation is generated, whatever the hydro PHIJ is the hydro generation, should be equal to the load at the ith time interval. Right? So this we have to ensure at every time interval that the total generation should be equal to total load. The second equation is very simple, that all the thermal generators should generate between its maximum and minimum capacities. Again, the next is also very easy. Hydropower plant, it should generate between maximum and minimum capacity of its generation. The next is the critical one, which is Q. So here Q means Qij is basically the discharge of the water. So the discharge should be limited by this Q max and Q min. So obviously whatever maximum discharge it can do and minimum discharge it can do, based on its previous study from the long range problem, he can ensure what maximum discharge it can do. And here the sum of discharge for all the time intervals should be equal to Kj. Kj is the water availability of the jth hydro plant, and here water availability means basically the whatever is the water available in the dam. It is not that availability, it is the availability for that day, because let's say here we are running this problem for 24 hours. So for this day, based on the long range scheduling problem, they could have got some estimate that how much maximum water we can discharge on this day, because he has to save the water for the next day also and for the later days of the year also. So he will ensure what is the water availability for today's operation. He will plan that water availability, and based on that he will ensure how much discharge is allowed. So the total discharge should be equal to that Kj, and based on this Qij max and min, it will be decided how much discharge will be there in per time interval. So this time interval, let's assume it can be a hourly time interval, it can be 15-minute time interval also, because India is a 15-minute market, so generally it is a 15-minute time interval. So based on this small time interval, they will be planning the discharge of the water. Right, so this model is clear to everyone, right? Any queries here? Any queries on this model? Okay, if no queries, then let us see how to solve this model, and with this we'll close this today's session, because hydrothermal is just a very small class. So what we are doing here is basically we can to solve this problem, the simplest step to form the Lagrange function. So this is the Lagrange function I have formulated. So here lambda is the dual for the power balance equation, gamma is the dual for the discharge equation, and rest all are the limits of maximum and minimum generation limits as well as the discharge limits. So we will not include that in the Lagrange function. So this is the Lagrange function. Now here lambda and gamma are the Lagrange multipliers, which actually ensures that these equality constraints are satisfied. And Q here, generally Qij, this I missed in the previous slide. Qij is equal to Phij, which is the power generation by hydropower plant, in this quadratic sense. So there can be various factors. Either you can take this discharge in the quadratic sense, or in the linear sense, or in the constant sense. So whatever will be, you can it is different assumption what different hydropower plant owners take, but generally it is taken as a quadratic, because if you take quadratic, it is mostly the correct assumption of the factor. You can also see here that A naught J is there, which is the constant discharge which will happen even if pH is 0. So can you guess here why this A naught J is there? A naught J, what is the reason of A naught J? Why do we want to discharge if my power generation is 0?
Because I think the overflow will be, because they have a set point.
Overflow, okay, that could be one of the reason. Yes, overflow can be reason, but basically there is also regulatory norms are there that you have to discharge the water. Basically you cannot stop the water from flowing in the river. So you have to, as I said earlier, that cities and agricultural lands are there in the downstream of the water, and they need water for their day-to-day activities. So basically you cannot stop the water, and therefore you have to anyway discharge some quantum of water, which will be A naught J, and then this BI and CIJ will be taken care based on the level of hydro generation. So if the hydro generation increases, the water discharge increases. So that's why this A naught J is there, right? So this is the
Sir,
way. Huh.
what about the head of the water? I think it is not included in this
Yeah,
formula.
yeah. So we have assumed head as a constant. Means in the previous slide I was mentioning that we have assumed head as a constant, and that is the assumption what we have taken. Obviously, practically, yes, practically you have to consider head also. You have to also consider the river inflow, the water inflow in the dam. So that also you have to take care. So a lot of factors are there which you have to consider in practice. But theoretically, I have ignored, or I have considered head as a constant, right? So yeah, I think I'll not be able to complete it. So this is just the algorithm. You can obviously solve this problem using any of the previous methods, because it's a quadratic problem. So you can either use the Newton's first order method, Newton's second order method, interior point method. I'm just explaining here the simple lambda iteration method what we have seen in economic dispatch. I'm showing that method here. So basically you have to just take the derivatives in terms of like lambda, gamma, ptij, phij. So you will take the derivative of all the equations or this Lagrange functions, and you will get this term. This is the equality equation. This is the equality equation for the discharge. This is the conventional thermal power generation formula. And when you take the derivative in terms of hydro, you not get only lambda, you also get the gamma j as the term. And this is the four equations, and you have basically the variables, and you can easily solve this problem by basically solving the simultaneous equations, right? As you were solving it for economic dispatch, the same way you can solve this problem as well, right? So this is very simple. I'm not going to detail here. Only thing what I want to explain you here is this lambda. We were discussing that this lambda is actually the price of power generation, right? It is in the rupees per megawatt. The dimension of this is the price of generation power either by thermal or hydro, and this price will remain same. So if you keep the equation, if this equation you make it in the equal to 0 and make it, so lambda will be equal to this df by dpt, and again here below in the fourth equation lambda will be equal to gamma dq by dph. So here also it will be there, and here I'm adding this dq by dph because q is also a function of ph, so that's why this dq by dph will also be there. So lambda is actually the price for generating power either from thermal or hydro, and that will be same for all the generators in this situation. And this gamma j, if I say gamma j is the price of the water, you can say that although we say that water is priceless and it does not have any price, but if we want to calculate the price of water at which the generators are facing or calculating all these factors, gamma can be a representative price of water rate in terms of rupees per megawatt or rupees per discharge, right? So if you see the dimension of gamma, it will be rupees per discharge. right? So you can easily calculate the dimension of gamma will be lambda and into pH by Q. So lambda has rupees per megawatt, so if you multiply it by pH it will be rupees, and Q is discharge, so Q is the discharge or the volume of water. So rupees per volume of water is actually represented by gamma, right? And this will be the price of the water for, and this will be different for all the hydro generators, right? So with this I'll stop this today's session, and we will discuss some numericals in the next class, and then with this we'll close the hydrothermal scheduling, and then we'll start the new topic.